Hi, everyone, and welcome back. It's Kira Garfola with Greenville Tech's Math 109. Today, we're going to talk about section 4.3, which covers one-to-one and inverse functions. Again, like last section, I tend to think that this is a simpler section than some of the ones that we cover, but there are a few sticky points, so make sure that you take some notes, follow closely, and as always, practice, practice, practice. So what is an inverse function? We say that two functions f and g are inverses if f of g of x is x and also g of f of x equals x. So both of these conditions must be met. You want to test f of g of x and you want to test g of f of x and make sure that they both come out to be exactly x. If one is x and the other isn't, no luck. It's not an inverse. We denote the inverse as what looks like f to the negative 1, but really that's just read as f inverse. That negative 1 in our text and in our course, when it's attached to an f like that, is always going to be the inverse function. So let's look at an example. We can use the formulas to convert degrees Fahrenheit to degrees Celsius and vice versa to demonstrate our inverses. These are actually going to be inverses of each other. So to get Celsius to Fahrenheit, we're going to have f of x equals 9/5 x plus 32. And to get Fahrenheit to Celsius, we're going to get g of x is 5/9 times the quantity of x minus 32. So first, let's verify that they are inverses. Our first step is going to be to find f of g of x. So f of g of x can be found as 9/5 times 5/9 x minus 32 plus 32. Take a moment, make sure that makes sense because that's a lot of numbers. But if you look, we're just plugging in g of x, so this quantity, right here where this x is in f of x. And now it's just a matter of basic algebra and arithmetic. We need to simplify that out and make sure that we get x. So all that math, this right here goes away. 9/5 times 5/9, those are reciprocals, so they become 1. So all we're left with is x minus 32 plus 32. And that is going to indeed simplify to x. So f of g of x we know equals x. Now we need to go the other way and find g of f of x. So g of f of x, anywhere that we see x right here, this quantity of f of x is going to be plugged in. So again, it looks kind of ugly, but it isn't really that bad. We can work through it algebraically. And if we look here, this is 9/5 x plus 32 minus 32. That 9/5 right here does not distribute. So this whole thing in here simplifies just to 9/5 x. So now we're left with 5/9 times 9/5 x. Again, with the reciprocals, those cancel out, and we're left with just x. So indeed, g of f of x also equals x. So we found that f of g of x is the same thing as g of f of x, which both equal x. So indeed, they are inverses. So a function is called one-to-one if every output of the function corresponds to exactly one input. So think carefully. This is a little backwards from what we did when we were talking about functions. When we talked about defining a function, we knew that every output had only, or every input had only one output, right? So for every x value, there could only be a single y value. Now we're saying we already know it's a function, so that's already true. But also, every y value only occurs per one input x value, okay? So for every y value, there is only one x. We know that a function, f, has an inverse if and only if it is one-to-one. So that means that if and only if means it goes both ways. So if it's one-to-one, we know that it has an inverse. And if it has an inverse, we also know that it's one-to-one. So let's look at an example of one-to-one. We want to determine here if the function is one-to-one. So we want to look at each output now and see if it belongs to only one input. So 4 belongs to -2, 1 belongs to -1, 0 belongs to 0. Here we see 1 again, and we see that 1 belongs to 1. Here it belonged to -1. So that's a problem. It's not 1-to-1 because we see 1 occurring twice and it occurs with different x values. The same can be said for 4. If you see the same y value multiple times, if its input is different, so if the x value is different, then it is not 1-to-1. Here we have 4 is associated with 2 and also -2. 2 and -2 are not the same number, so this function cannot be 1-to-1. There's a way to more easily do this, at least graphically, and we're going to use the horizontal line test. So remember that we used the vertical line test to determine if a relation was a function. So if we put a vertical line anywhere on that graph, that vertical line should only touch the function once. That is going to look for only one output per value of x. Now we're going to flip it and go the other way. The horizontal line test is going to tell us if a function is 1-to-1. So instead of using a vertical line, we're now going to use a horizontal line. Does that horizontal line hit the graph more than once? If it does, the function is not 1-to-1. So if it passes the horizontal line test, then we know that there is an inverse and we can find it. I have no idea why this is all jumbled at the top. That's very strange. This should say example horizontal line test. Sorry about that. I have a new laptop for work and I am going to assume that it got jumbled in some sort of file transfer. Interesting. So determine if the following function has an inverse. So here we're going to apply that horizontal line test. So can we draw a horizontal line anywhere and it touched that graph more than once? Take a moment and think about that. Here we see that blue horizontal line and it's hitting it once, twice, 3 times right here. So it is not 1-to-1. It cannot have an inverse. Let's think about another example. Determine if the following function has an inverse. We're going to have f of x equals x cubed plus 5. The easiest way, in my opinion, to do this would be to graph it. So take a moment and graph the function x cubed plus 5. You may have to zoom in to further examine some areas, especially when you see cubics, or if it's to the 5th or if it's to the 7th, any of those odd powers, the higher you get, the flatter it gets in the middle. But it's important to zoom in and see that it's not actually perfectly horizontal. So yes, we should see that it passes that horizontal line test and it must be 1-to-1. So it has an inverse. If you give me just one moment, I will show you. Let's see. I'm going to use this again with my new calculator on here, or my new computer, excuse me. I don't yet have the calculator emulator sorted out. So I'm going to go ahead and show you here. What was that function? X cubed plus 5. So if we look here at the graph, we can see that we can draw a horizontal line anywhere. The only questionable area is right here. And if we zoom way in, way in, it looks like it might be flat, but it isn't actually flat. So that horizontal line isn't actually problematic. And you can continue to zoom if you want. And you'll be able to see that it is not perfectly horizontal. Let's see if I can do this. Let's do 4.9999 to 5.0000. And you can just keep zooming in. And the further you zoom, the more you're going to see it doesn't ever dip down and go across. So it is not horizontal here. So it passes that horizontal line test, and it means that it must have an inverse. It is a 1-to-1 function. So we know that it has an inverse. So what do we do with that? How do we find the inverse of f? We're going to follow these steps. They're pretty simple. They're an exercise in algebra. It's college algebra class, so no surprise there. First, you're going to make sure that it does have an inverse. We've already done that for the last one, but go ahead and graph it, take a look at it, make sure it passes that horizontal line test. Then you're just going to switch the places of x and y. So if it's in form of f of x equals something, remember f of x and y are interchangeable. So flop your x and your y, and then you're going to solve for y. Voila, that's your inverse function. Let's look at an example here. We want to find the inverse of the function f. So we have f of x equals 3x minus 2. So that could also be written as y equals 3x minus 2. We're going to flip our x and our y, so x equals 3y minus 2. And all we're going to do from here is solve for y. We would get x plus 2 divided by 3 equals y. That is our inverse function. If we want to write it back in the original terms, f inverse of x equals x plus 2 over 3. Take a moment, make sure you can replicate that. It's a fairly simple example, but it's good practice. Now, if we graph our inverse, we're going to notice something curious. This red line was our original, okay? This red increasing line was 3x minus 2. This blue line is our inverse of x plus 2 divided by 3. If you look carefully, this dotted line here is y equals x, just the identity function. And if we actually flip, we rotate it around this y equals x. If we use y equals x as a mirror point, that is going to give us our inverse function. So it is symmetric around y equals x if it's the inverse. Now, something else you can take note of here. Our original was 3x minus 2, and the inverse is kind of undoing, right? Like what do we need to do to it to undo it? You have to be careful with the order that we do things, but when you look at your final answer, it's a good way to check it. 3x minus 2, to kind of undo that, we would want to add a 2 somewhere, and we want to divide by a 3 somewhere. And sure enough, we add the 2 up here, and we divide the whole thing by 3. It turns out that this graphing of inverses is always the case. Any function's inverse, the graph of it is just reflected across y equals x. So take a moment, pause the video, and see if you can find the inverse to f of x equals x cubed minus 8, and then also graph it. Okay, so let's look at the solution. First, we're going to say y equals x cubed minus 8. We're going to switch our x and our y, and we're going to solve for y. This is going to give us y equals the cube root of x plus 8. That means that f inverse is the cube root of x plus 8. So there's our algebraic answer. Let's graph the original and the inverse at once. Sorry for that. Again, new computer troubles. So graphing our functions, our original is the red, okay? This red right here, this steep increase, is x cubed minus 8. This blue version is the inverse. It's the cube root of x plus 8. And here again is y equals x on that line. And you can see if you kind of tilt your head that there is a reflection. If we folded this graph over perfectly on y equals x, these graphs would stack on top of each other, right? There's a reflection here and there's a reflection here. If you didn't get the correct answer, make sure you go back, pause again, and find your mistake. It's probably algebra. So that's actually it for this section also. Another short section in a row. And in conclusion, just remember that to determine whether a function has an inverse, you need to look at the outputs. If it has more than one input per output, there's no inverse. In other words, if it's not 1-to-1, there's no inverse. If it fails that horizontal line test, there's no inverse. Each y should only be associated with one x. If you want to find the inverse function, you're going to swap x and y, and then you're just going to solve for y. And if you're looking graphically to see if two functions are inverses of one another, you want to look and see if they are reflected across or if they are mirror images of each other against y equals x. So remember the symmetry that we've talked about in a previous section, the symmetry on X, the symmetry on Y. This is the symmetry on Y equals X, that diagonal line. As always, practice, practice, practice. It'll be very important. You will see these again on homework tests and beyond. So take advantage of the short sections, get the practice that you need. Again, if you need more help, more resources, there's a ton of stuff in Blackboard. I'm available in office hours and email. You can stop by and visit me. And the Math Center is always there to help. If you're struggling, shoot me an email and we'll go from there. Thanks again, and I hope to see you next time.